Okay, in this video, we're going to be talking about square roots, cube roots, nth roots, different roots. So first, let's talk about evaluating square roots. Just so you know, when you've written the square root symbol in your life, there was an invisible 2 there that we never really mark. We don't really put the 2 there because it's assumed, but the word square indicates that this is a 2 right there. So this is the type of root it is. Keep in mind that the square root of a number is equal to this only if the number that you come out, if it were squared, you would get the number back under the radical. Okay, so it's like the inverse of squaring. All right, if you put a negative in front of a root, then you put the negative in front of your answer. If there's a negative inside the square root, if it's a square root specifically, then that -1 is actually representing an imaginary number. Okay, so you get your answer out and then an imaginary number. That's because I is defined as the square root of -1. We'll talk about that a little bit more later. All right, so basically what happens is when you're trying to simplify a square root or a cube root is you want to use your factor tree and pull out pairs. Now the reason we're pulling out pairs is because this is a square root. If it were a cube root, you would pull out sets of 3. If it was a 5th root, you would pull out sets of 5 and so forth. So basically you have to look at what kind of root you have to determine how many duplicates you need to pull out. So here's the square root of 16. Now I happen to know that the square root of 16 is 4 times 4. You could have written 8 times 2. It's okay. You would have eventually gotten the same answer. It's okay. In this case, by writing 4 times 4, I found a pair of the exact same number. So because 4 times 4 will give me 16, the square root of 16 is actually 4. So when I pull out a pair, I only pull out one of them because the square root of 16 is clearly not 16. If I pulled out both of them, I would say the square root of 16 is equal to 16, and that's not the case. Okay? All right, so let's look at if you had a fraction. Well, the square root of a fraction, as long as the whole fraction is in the square root, is the same thing as the square root of the numerator divided by the square root of the denominator. So you can take the roots of the numerator. This happens to be 2 times 2, so you pull out a 2. And this is 3 times 3, so you pull out a 3. And then that would be your answer. Remember, if you have a negative in front of the square root, you just keep the negative in front of your answer. Here I found a pair of 7s that multiply to get this. So I can pull one of the 7s out. Remember, if you take the square root of something that is squared, it's simply that same thing back because the square and the square root are inverses of each other. You're basically canceling them out by doing both. So in this case, the square root of something squared is that same thing pulled out. The square root of this thing squared is simply this pulled out, because they're inverses. The square root of this, I can factor this out to be 5 times 5, or 5 squared. And this is the same thing as x cubed squared. I rewrote it in terms of a perfect square. So the square root of something squared is that thing. The square root of something squared is that exact thing pulled out. All right, so try these. Okay, hopefully you got -7 for this. This is 7 times 7 is 49, and x to the 5th squared is x to the 10th. And then this becomes x plus 8, because anything squared and square root, you just get the same thing back out again. All right, let's talk about cube roots. Cube root is kind of like a square root, except that instead of looking for sets of 2, you're actually looking for sets of 3. When you find your set of 3, you only pull one of them out. So the cube root of a number is equal to that number only if that number cubed gets back to your original number. So here's an example, the cube root, and in the cube root you would have to write 3. You can't just assume it. It would be a square root if you don't put anything. So you're looking for something that factors out. All right, so first of all, let's get this negative. Now before, when we had a square root of a -1 that equaled I, that's basically only for even roots. All right? For odd roots, it's equal to -1. because you could actually multiply a negative times a negative times a negative and get a negative inside of there. So this negative 1 is the same as negative 1 times negative 1 times negative 1. So you actually get to pull out a negative 1 because there's a set of 3 negative 1s here. So let's look at the 64. The 64, I factored it. You may have factored it a little bit differently. But basically, I factored it into several different pieces, and I'm looking for sets of 3. So I found a set of 3 2s. I found another set of 3 2s. I found a set of 3 x's, so I pulled out an x. I found a set of 3 negative 1s, so I pulled out one of those. And then I just multiply my answers together because nothing's left under the radical. And that's my answer. All right, so looking at this one, I kind of started breaking it out for you. This is the same thing as the cube root of negative 1. Since it's odd, you can have negative 1, and the cube root of negative 1 is negative 1 because there's 3 negative 1s multiplied together to give you negative 1. This is the same thing as saying 3 times 9. So I have a set of 3 here. And this is the same thing as saying x times x times x, or the cube root of x cubed. So I have a negative 1, I have a negative 3, and I have an x that I'm going to pull out. Because remember, I'm looking for sets of 3, and I pull one out. Sets of 3, and I pull one out. Sets of 3, and I pull one out. Okay, here, kind of the same idea. You take your fraction, and you cube root both the numerator and the denominator. So this numerator is the same thing as saying 1 times 1 times 1. And the denominator is the same thing as saying 5 times 5 times 5. So the answer is 1/5. This last one, remember, it's an odd root, so it's okay. So let's just expand it down here. We're going to get equals the cube root of negative 1 times the cube root of, positive 8. Okay, in the numerator. And in the denominator, we have the cube root of 27. Okay, and based on our factor tree up here, we know some of this information. So this is just going to be negative 1. This is going to be a 2 because 8 is 4 times 2, which is 2 times 2. So there's 3 2's in there, and that's where the 2 came from. And then in the denominator, we got a 3 because the cube root of 27, as we showed up here, is 3. All right, so let's talk about just regular nth roots. It doesn't have to be square root. It doesn't have to be cube root. It could be any kind of root. All right, so technically, if it's an even root and there's an odd underneath here, it's the absolute value. We don't go into that so much this year, but you'll go into that in your next course. So basically, whatever the root is, you're looking for that many sets, as we talked about before. Since this is the 4th root, we need 4 of something to pull out 1. All right? So that's why the 3 comes out. We're looking for 4 of something to pull out 1. Now, the difference between this one and this one is this minus sign out front. Remember, the minus is not part of what's happening inside the radical, so you just keep it on the outside. We talked about this just a moment ago. If the root is even, then the square root of negative 1 is I. But if the root is odd, then the square root of, the nth root of negative 1 is simply negative 1, because you can actually multiply negative 1 in an odd number of times and get negative 1, so you're fine. So here's the 5th root. That's an odd root. N is odd. So since n is odd, this becomes negative 1, so we can have a negative 1 here. That's what gets pulled out. And then you factor your 32. We're looking for sets of 5. So here we got 5 sets of 2, or excuse me, a set of 5 2's, right? So I can pull one of the 2's out, and this is my answer. But look, if I had put the negative underneath the radical with an even root, there's no way to get a set of 4 of something that will multiply to give a negative number. So this turns into I because of this even root. There's no way to get 4 numbers that will multiply to get a negative number, because negative times negative is always positive. So then I go ahead and factor out my 32. I get 4 sets of 2, because I'm looking for sets of 4. There's 1 left over. So this leftover 2 is stuck under the radical. I can't do anything about it. But this set of 4 2's, I pull one of the two out, and it gets to be on the outside. Let's practice a few. Okay, so hopefully as you worked it out, if this and this are the same, you end up getting the same answer, but let's just work this out. This would be like 5 x's multiplied together. 1, 2, 3, 4, 5. I'm looking for a set of 5, and guess what? I got it. All right, let's look at this one. This is negative 6 cubed, which is the same thing as saying negative 6 times negative 6 times negative 6. I'm looking for a set of 3, and guess what? I have a set of 3. And since it's odd, I can actually do that. Negative times negative will give you negative. All right, again, this is an odd, so I could split this up into negative 2 times negative 2 times negative 2, and then I can split this guy up into y times y times y. That's what y cubed is. So I have a perfect set of 3 here and a perfect set of 3 here. Now this is the square root of something squared. So again, this root and this power are exactly the same, so I'm just going to get the answer out that I put in. This is the same thing as saying cube root of 1 over the cube root of 1,000. So the cube root of 1 times 1 times 1 is 1. So I can pull a 1 out of the top. That's a set of 3. And this is the same as 10 times 100, which is the same as saying 10 times 10. I have a set of 3 tens. So that will be my answer. All right.